So the next topic we're going to talk about here is satellite motion. Okay, and to intro this topic, I want you to think about a situation where a person is throwing an object, all right, from some height, we'll say 5 meters here, and they progressively throw it with a greater and greater speed. All right, we know from projectile motion that it's going to travel some horizontal distance, it's going to drop that 5 meters and eventually hit the ground. But I want you to consider the situation where they're throwing it ridiculously fast. Okay, like faster than what is actually humanly possible. And think about that projectile going a really, really, really big distance. You notice here, and you're kind of seeing this in the diagram, that eventually when we throw it far enough, all right, after it's dropped 5 meters, it still hasn't hit the ground. And the reason is it's traveled so far that the curvature of the earth here is actually starting to come into play. That's what this diagram is showing. So imagine something that's traveling so incredibly far, like something that's going from, say, Philadelphia all the way to Los Angeles. And the curvature of the earth is actually coming into play in that situation. We can't treat the earth as this flat object because it's over such a big distance that we actually notice and see the curvature of the earth. We're going to take this example one step further to think about what it means for an object to be a satellite, to be in satellite motion in orbit. So we're here once again, and we have a cannon now firing from the top of a mountain. And we see that progression where we're traveling faster and faster and firing it with greater and greater speed, and the curvature of the earth truly is coming into play. And then we hit this point here, this path right here. Okay? And what you're seeing with this path is you're seeing the object, okay, has been fired. The object is in free fall. All right, it's being pulled towards the center of the earth at 9.8 meters per second squared. But what has actually happened is it is traveling so fast that even though it's constantly falling towards the center of the earth, it never actually hits the center of the earth. That path that it takes, that curved path, is the same as the curvature of the earth, and so it never actually gets closer to the earth. And if we fire it faster, obviously we take a slightly more elliptical path, and we'll talk about that in a little bit more detail in a second. So here's the basic idea of satellite motion. As we were talking about in the last slide, satellite motion is a situation that occurs when an object is moving so fast, it's basically a projectile that's fired so fast that even though it's constantly falling towards the center of the earth, it never actually lands, it never actually hits the earth. So this object, this satellite, is constantly falling towards the surface of the earth, towards the center of the earth actually. But every time it falls, whatever distance it would need, whatever height it started above the surface, the earth itself has curved away. And so it's in this perpetual state of free fall, all right? It just never manages to reach the ground because its motion, tangential to the surface of the earth, is so great that it actually begins to orbit, okay? And so what we're ultimately left with is a situation that's a combination of free fall and circular motion. That's what orbit really is. We have that inward force of gravity constantly pulling the object towards the center, but like we said, it's traveling so fast that it never actually hits that, and it begins to go around the earth. So we're going to have this inward acceleration that we talked about with circular motion. I should point out that not all orbits are circular, but a lot of the ideas that we talked about with circular motion are going to apply to non-circular orbits as well, and we'll look at that as we go through this unit. So for the next part, we're going to talk about Kepler's three laws, which, much like Newton's three laws, are going to define this motion. Okay, Newton's three laws tell us about forces. Kepler's three laws are going to tell us about satellite motion. So we begin Kepler's three laws, which were named after Johannes Kepler, who was an astronomer and did a lot of work on the orbit of planets. But we begin with this first law, which tells us that all orbits have elliptical paths, with the sun, or the center of its orbit, if it's orbiting, say, a planet instead of the sun, as one of the foci. So what does that mean? Just a quick geometry refresher here. A circle is a shape where every single point is the same distance, all right? We call that distance the radius, from a point which we call the center here. Okay, so that's what the definition of a circle is. Every point is the same distance from this central point. With an ellipse, rather than having one central point, we have two. We have two foci, the plural of focus. Okay, and every point on the ellipse, the sum of the distances. So I'm going to call those D1 and D2. The sum of the distances from each focus to the point on the ellipse is the same. Okay. But obviously those individual distances vary. So that's what an ellipse is. So every single point on this ellipse, if we added up the distance from this point on the ellipse to the sun and this point on the ellipse to this other focus, that would be a constant number. So Kepler's first law tells us that all planets follow this elliptical path, okay, where the sun is one of the foci, and then the other focus is just some point in space. It really doesn't have any significant meaning. Okay, but the sun, or whatever the central object is, like I said, if it's a planet, is one of the foci of the ellipse. All right, moving on to Kepler's second law. So Kepler's second law tells us that planets sweep out equal areas in equal amounts of time. So if we think about a planet orbiting here, and we'll say it's orbiting in a counterclockwise direction, here's what that means. When we say the planet sweeps out an area, what we're talking about is as the planet moves from A to B here, we're thinking about this sector, okay? That's the technical geometric name for it. But this sector, or this pie slice really, that is swept out, the area basically covered by a line going from the sun, or whatever the central object is, to the planet as the planet moves here from B to A. So that would be the area swept out going from B to A. And then if we're closer to the sun, as we are here at C, this would be the area swept out from C to D. So what this diagram is showing is it's showing these two sectors, these two pie slices here, being equal. And Kepler's second law tells us that if those areas, the area swept out by the planet, is equal, that means the time it takes to travel from here to here is the same as the time it takes to travel from C to D. So what does that ultimately translate into? What that ultimately means is that planets are traveling faster when they're going closer to the sun. If we have an elliptical orbit like this, it means that the planet's going slowly as it's out here far away. And as it gets closer and closer, it speeds up, and then it slows down as it gets further away, and then it speeds up as it gets closer and slows down again. So the orbital speed is not constant when we have an elliptical orbit like this. They travel slower here, all right, than they do here, because when they're further away, they don't have to travel as far to sweep out the same area as they do when they're very, very close to the sun. And so that's what Kepler's second law tells us. All right, the third law tells us conceptually that planets that are further from the sun take longer to orbit. We will have an equation here for this in a second, but the further away a planet is from the sun, the longer it takes to complete its orbit. So we think about our solar system here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto before was recategorized as a dwarf planet. What I always learned was my very educated mother just sat upon 9 pizzas. Okay, if we think about those planets, this third law tells us that Mercury will take the shortest amount of time to orbit the sun, and it does, about 88 days. And then Venus, I believe it's 200-something days, then Earth, then Mars, then Jupiter takes something like 11 years to orbit, Saturn, Uranus, Neptune, and Pluto. Pluto takes over 200 years to orbit the sun once. It's actually a fun fact about Pluto. From the time that it was discovered, all right, it was the last planet discovered, until the time that it was reclassified as a dwarf planet, it didn't even get to go around the sun one time. Okay, that's how long it takes Pluto to orbit. So that's what Kepler's third law tells us, is that planets that are further from the sun take longer to orbit. We can derive a mathematical relationship from this by combining circular motion with universal gravitation. We're going to skip right to the final result here, but the equation you're going to see that supports this conceptual notion can be derived from combining those two things. So mathematically, Kepler's third law looks like this: T squared, where T is the period of orbit in seconds, is equal to 4 pi squared times r cubed, where r is the orbital radius, or the average distance between the central object, so a lot of times the sun, but not necessarily the sun, and whatever's orbiting, divided by g times big M, where M is the mass of the central object. So again, if we're talking about the planets orbiting the sun, this M is going to be the mass of the sun. If we're talking about things orbiting the Earth, this M would be the mass of the Earth. It's always the mass of the central object. So this is Kepler's third law, okay, a mathematical relationship between the period and the average orbital distance, okay? And we see on the most basic level, as the period increases, so does the average orbital distance, but more specifically we can say that the period squared is directly proportional to the average orbital distance cubed. So there we have the mathematical form of the third law. Few really important points to keep in mind here with the third law. The first is that r is the radius of the orbit, okay, not the radius of the object itself. It's the radius of the orbit, or the circular path taken by the object while it's in orbit. Okay, that's what that r stands for. So that's one important thing to keep in mind. The second is the mass is the mass of the central object. Again, the thing that is being orbited. If we're talking about the moon, it would be the Earth. If we're talking about a planet, it would be the sun. We are making an assumption here, and that is that the mass of the central object is significantly more than the mass of the objects orbiting it. And that, for the most part, is going to be true for all the situations that we deal with. It's absolutely true for the sun relative to the planets. The sun is about 1 million times more massive than Earth. It's true for Earth relative to the moon. Okay, so we're really not going to deal too much with situations when it's not true, but that is the assumption we're making. If we did have a situation where it's not true, what ends up happening is we'd use the total mass of the system, and we think about the orbit of both objects around what's called the center of mass, which is something that we'll talk about a little bit later in the year. The other really important thing to keep in mind here with the third law is that your period must be in seconds and your radius must be in meters, okay? All the constants we use rely on period in seconds, radius in meters. Yes, this is slightly frustrating because we're talking about the orbit of planets, which can take years. We're talking about distances that are millions of miles that we have to have in meters, but that's the way it is for this version of Kepler's third law. I want to take a second now to rearrange slightly Kepler's third law. And what I'm going to do is I'm going to divide both sides by this r cubed here. And so what I'm going to end up getting is t squared over r cubed is equal to 4 pi squared over gm. And the reason why I did this is, if we think about this right side of the equation now, if we're talking about two things orbiting the same object, okay, so for example, Venus and Earth both orbiting the sun, okay, this term here on the right-hand side is going to be a constant, okay? 4 is not going to change, pi is not going to change, g is a constant, and this m is the mass of the central object. So if they're orbiting the same thing, that would also be the same. The reason why this matters, the reason why this is useful, is it tells us that this ratio of t squared over r cubed is going to be a constant for all objects orbiting the same thing. Okay? So if we're comparing, like I said, two planets in our solar system both orbiting the sun, that ratio would be the same. And so what we can do is that allows us to rewrite Kepler's third law. And so here we have an alternate form of Kepler's third law, which says Ta squared, so the period of object A squared over the orbital radius of object A cubed, equals the period of object B squared over the orbital radius of object B cubed. And so this allows us to compare the period and orbital radius of two different objects orbiting the same thing. We just saw that this is a constant, which is the reason why it works. Here's why it's really useful. Is when we're using this, okay, this form of Kepler's third law, we don't need to convert to seconds and meters. This is a ratio. Those units are going to cancel out. And so as long as we have the same units for both periods and the same units for both radii, it doesn't matter whether those units are seconds or minutes or days or years or whatever. And same thing with the distance. It could be in miles, it could be in kilometers, it could be in some other unit. Okay, so that's really the useful part of this. All right, this ratio form of the equation is great if we are comparing two things orbiting the same central object. Before we do a few problems, just real quick, I want to talk about the difference between the two versions of Kepler's third law. Okay, that first version we learned, we're going to be using that when we're only concerned about one object. We only know about one object orbiting the central object. We will need the mass here of that central object in order to be able to complete this, so that's something to keep in mind. And we need to have our units in meters and in seconds, so that's the other thing we want to keep in mind. The other version, the ratio version, is great when we're comparing two objects orbiting the same central object. In this case, we don't need to know what that mass of the central object is. We just need to know about the two objects orbiting it. And the other benefit to this one is we can use any units. Alright, so we're going to go ahead and try a practice problem here. So for the first part of this, we want to calculate the length of a year on Mars, meaning the time it takes Mars to orbit the Sun using our planetary data. So we're going to start with Kepler's third law here. T squared equals 4 pi squared r cubed over gm. And basically we're just plugging in the things that we know. So the radius, which is the average distance, looking at our planetary data, is going to be 2.28 times 10 to the 11th. Okay, if we think about the Sun and Mars, whatever that distance is, that's going to be the radius of the orbit. And then we're going to divide by big G, which is our constant, 6.67 times 10 to the negative 11th, times the mass of our central object, which in this case is the Sun, so 1.99 times 10 to the 30th kilograms. Okay, so we're going to go ahead and calculate this. We have everything in the proper units because our radius is in meters and our mass should be in kilograms. Just be a little bit careful with parentheses. That sometimes can be the thing that messes things up. We want to make sure we have that entire bottom part in parentheses. This is also a good time to remind you about the EE button, which I think makes your life a lot easier. That second comma, which allows you to replace the exponent. So if I were you, in my calculator, I would type it in like this: 4 pi squared times 2.28 E11 cubed. You can type it in just like that. And then we're going to divide that by, and I would put in parentheses, 6.67 E negative 11 times 1.99 E30. All right, and that should output the right answer. And when we solve for t, doing that math and taking the square root, I get 59373504. Okay, so 59,373,504, and our units are going to be seconds. All right, so that would be the length of 1 year on Mars. Since that's kind of a ridiculous number, we could go ahead and convert this. So we can say 3,600 seconds is 1 hour. We know that 24 hours is 1 day, and we know that 365, technically 365.24 days is 1 year. And we can go ahead and convert all of that, and we end up getting that this period in Earth years, okay, 1 Martian year in Earth years would be 1.88 years. Okay, so it takes just under 2 years for Mars to go around the Sun once. For part B here, we're going to go ahead and try and find the average velocity of Mars as it orbits. So we're actually going to use an equation that we use during circular motion to find the velocity of an object moving in a circle. I realize that Mars's orbit is not perfectly circular, but it's close enough that it's not going to make a significant difference if we assume it to be circular. Most of the planets actually have very circular orbits. So I go ahead and plug in the average distance, which is the radius of that orbit, 2.28 times 10 to the 11th, over the period. And I do want to keep this in seconds because I want to get that velocity in meters per second. And so when I do that, I find that Mars is traveling around the Sun at a speed of 24,128 meters per second. So moving at a pretty good clip there. All right, one last practice problem here with Kepler's laws. And so we're looking at a fictional planet here that has 2 moons named Calvin and Hobbes orbiting it. Calvin has an orbital period of t, and we know that Hobbes is 2.4 times further away than Calvin. We want to find the orbital period of Hobbes. So for this one, this is a great one to use our comparison equation here because we don't know anything about the central object, but we do have information about 2 objects orbiting the same thing. So I'm going to say A is going to be Kelvin here, and B is going to be Hobbes. So I'm going to say that the period for A, which is Kelvin, is just defined as T, divided by the radius. I don't know that, so I'm just going to leave that as R cubed. I'm solving for the period for Hobbes, so I'll call that TH squared. And then the radius is going to be, I don't know either one, but I do know that this radius is 2.4 times as much. So it's going to be 2.4, that entire quantity cubed. So I end up with T squared over R cubed equals the period for Hobbes squared over 13.82 R cubed. Okay. The r's can actually cancel out there, the r cubed. Notice that I cubed that 2.4 as well. That's really important. And so what I'm left with here is t squared equals th squared over 13.82. Multiply both sides by 13.82, and then I'm going to take the square root of both sides to solve for th. And so I end up getting 3.7t is equal to th, the period for Hobbes. So it would be 3.7 times longer, given that it's 2.4 times further away.